In this project, we designed a system to reconstruct objects that are continuously deforming in front of a single depth sensor. Note the considerable deformations in the sequences that we consider. Despite this, we are ultimately able to fuse this data into a high-quality model. This is accomplished by explicitly detecting loop closure constraints to compensate for drift and sensor tracking, and by using a bundle adjustment algorithm to compensate for the non-rigid deformations. Now we show the system pipeline. Our system starts with a sequence of color and depth. Note the dramatic deformations in this sequence. In the first stage of our system, we fuse short subsegments of the input sequence into a set of partial scans. In contrast to naively fusing the entire sequence, where drift will be a problem, these short segments can be fused reliably. In addition, each partial scan provides a compact summary of the data in the frame, dramatically reducing the computational complexity of later stages. In the second stage, we compute a coarse alignment of the partial scans. We set the first scan as the reference, and consecutively deform each of the remaining scans to align with the reference scan. As expected, the loop closing causes significant issues, manifesting in the appearance of duplicate noses and arms in the coarse alignment shown here. In the third stage, we detect loop closure constraints and redistribute any alignment errors over the loop. As shown on the left, the alignment dramatically improves after loop closure. Volumetric fusion of these scans then produces the mesh shown on the right. Unfortunately, this step fails to fully minimize alignment error, so alignment artifacts are still visible. The final stage represents our main contribution, where we run a bundle adjustment-like algorithm to optimize for both the final mesh and deformation parameters. Following a coarse-defined strategy, we first run this bundle adjustment with a low-resolution mesh. Note the increase in detail on the right forearm and hand. Next, we run the bundle adjustment again with a high-resolution mesh to recover the finer details. Here is our final reconstruction after bundle adjustment. Our system is also able to perform full body scanning from a single depth sensor while removing many of the restrictions of previous work. We demonstrate here that scanned subjects can casually perform a full turn in front of the depth sensor, removing the need for carefully orchestrated movements. The result of our system is nonetheless a high-resolution mesh that has explicitly accounted for the non-rigidity in the system and integrated the majority of the data available. In contrast, the 3D self-portrait system requires the user to hold still and wait for the system to finish a static scan, and then to turn around for other scans. Here, on the left, we show the scan results from the 3D self-portrait system. The right is from our system. Since our system allows for continuous motion, it fuses data from more perspectives and results in more facial details. Our system is also able to scan objects other than human beings. This sequence of a coat has many deformations while being rotated. The middle shows the surface after loop closure, and the right shows the final mesh after bundle adjustment. Here are more scanning examples. Note deformations in the input sequence. These are the final meshes after bundle adjustment.